Okay, welcome back. Apologies for that delay. Excuse me. Well, what I want to look at is something called the Zener Diode. And one of the information that you will look at as electronics, in regards to electronics, is that you will need to produce circuits which utilizes the effects of the diode as a whole. Now, there's quite a few types of diodes, okay? But what I wanted to look at was how the diode first came into being, basically. That was just my own curiosity. So one of the first useful theories on the breakdown of dielectrics, excuse me again, the insulating material between the two conducting plates of a capacitor is called a dielectric. Now, I have a video already on my channel which talks about capacitors and the effect of the capacitor and dielectrics on a capacitor. Okay, so feel free to look at that if you can't remember what the effect of a dielectric is. Okay, so this was put forward in 1934 by Zener. Excuse me again. Now, he suggested that under the influence of a very intense electric field, 7 million volts per centimeter, electrons can tunnel through the forbidden energy gap. Now, what you have to bear in mind is that we could not get electrons to pass through a insulating material, because as it's an insulator, its electrons, well, its structure is more condensed. So what Zener found out was that if you applied a high enough voltage to a given material at a given thickness, that you can actually force these millions of electrons to go through that energy gap. And that is what he had discovered. Okay. Now, what I've done here is that I've put a lot of the writing up front, and I've brought the diagrams after. Okay. So in this case, we're going to be looking at a lot of text, and I'm going to be doing a lot of talking. But feel free to look at and do some additional research for yourselves as well. Okay. Now again, just recapping, he suggested that under the influence of a very intense electric field, 7 million volts per centimeter, electrons can tunnel through the forbidden energy gap. This theory is certainly true in semiconductors p-n junction diodes with a relatively thin depletion layer. Now what this simply means is that it's a very thin slice of a material which then, when you apply a given voltage to it, will actually allow the effect, Zener's effect, to happen. Okay. Just to recap, this theory is certainly true in semiconductors p-n junction diodes with a relatively thin depletion layer. When breakdown occurs with anode voltage in the region of minus 2.6 volts to 5 volts, my apologies here, to 5 volts. This kind of breakdown is known as Zener breakdown. Okay. Now it is here, it is minus 5 volts. because if you apply a voltage, it will both operate in the plus region and in the minus region. Again, do some additional research for yourself so you can see what I'm trying to say here. Okay. So okay, I've just been reading some additional information myself, and it gave me something slightly different, but the intention is still the same. With wide depletion layers obtained by modifying the impurities doping breakdown, doping breakdown occurs at a much higher voltage than is expected by Zener theory. Okay. Again, this guy Zener, that's you can identify now that the Zener Diode was named after him. Now again, I'm doing a lot of reading and talking here, okay? Because of putting the diagrams at the bottom, I want to try and get the text out of the way first, okay? In such cases, the breakdown mechanism is thought to be due to avalanche breakdown. The breakdown mechanism is explained as follows. Leakage current in p-n junction diodes is largely due to minority carriers drifting across the junction under the influence of the reverse bias. Now, if the electric field in the region of the junction is sufficiently great, the electrons are accelerated and acquire enough energy to ionize atoms by collision. They do this by stripping off valence electrons to generate electron hole pairs in the depletion layer. Now this is what Zener is saying, that if you produce a high enough voltage, you can actually drive these electrons through an insulated material. So you can take an insulating material, slice it in slices, and actually drive a current through it, and actually make electrons move through it. And that's what's happening here, okay? The effect is to cause a very rapid transition from a reverse blocking state to a reverse conducting state. Both avalanche and Zener breakdown diodes are both known as Zener diodes. Okay. Now, description of equivalent circuit. Now, diode D1 allows conduction in the conventional manner when the anode is positive with respect to the cathode. Conduction takes place through D2 when the cathode potential exceeds the breakdown potential Vz. Now, you will need to draw out the diagram for this yourself so you can see what it's been saying here. Okay, and again, as I've said, I've put the text before the diagrams, so you'll need then to link the diagrams in for yourselves to the written text. Okay. Now, resistance Rz represents the reverse breakdown slope resistance of the diode, which has a value between 0.5 ohms and about 150 ohms, depending on the operating point and diode rating. Okay. Now, the anode current of the 4.7 volt diode is largely composed of carriers which have tunneled through the potential barriers, and the characteristics is typified by a smooth knee. Now you will see here where it has tunneled, and again we're going back to Zener's theory of being able to tunnel through an insulating material, okay? And that's what's happening here. Now it's moving in. Now you'll see where the knee comes in when it goes, when I show you the graphical representation in regards to the Zener diodes, okay? As we've gotten further on, okay? Sorry about that. Sketch back into the light. Okay. Now, avalanche breakdown diodes have a characteristics with a sharp knee, which is due to the sudden transition from reverse blocking to reverse breakdown, and the slope resistance is generally higher than that of a Zener breakdown diode. Okay. Sorry about that. If we twist it off here a little bit. Okay. The voltage required for the Avalanche Zener diode is higher because it has to overcome a greater resistance value. Now, the voltage in regards to the Avalanche Zener diode is greater because you're almost trying to drive a current through a resistive material, but because the resistive material is that thin, we are able to drive it through anyway purely by electron movements. Okay. When breakdown occurs between 5 volts and 7 volts, there is a range of diodes whose breakdown mechanism is partly due to Zener effect and partly due to avalanche breakdown. Okay. Now, the forward characteristics of both Zener and avalanche breakdown devices are generally similar to a conventional PN junction diode. It is found that Zener and avalanche breakdown mechanisms react in different ways to change in temperature. Okay. Now, in Zener breakdown, the tunneling effect increases with temperature, resulting in a greater flow of current for a given anode voltage. Okay. In avalanche breakdown devices, the increased temperature results in increased activity in the atomic structure, and the free charge carriers find it more difficult to acquire the critical energy to ionize other atoms. So as a result, the breakdown voltage of avalanche diode increases with temperature. So what that means that if you have a high temperature in regards to the avalanche, it will take a higher voltage for it to break down in regards to that matter. Okay. Again, look back at the information. Let's just make sure that we have it all in. Okay. So we'll just recap back a bit. Okay. So all I'm going to do now is just go back a little bit to recap. Make sure that everything is in. It can be seen by just yourselves. Okay. Okay. Just recapping, okay? So nothing to do here. You should have done this already. It just make sure that you can look back at this in your own time and that all information is there for you to refer to, especially as the text has been written before the diagrammatical illustrations. Okay. I think we're there. Okay, yeah. Okay, so let me go back now. Go forward. Now I have to take the time to make sure that I do this, because sometimes if I don't do this, when you come to play it back, you find that your video moved unexpectedly and pieces of it have missed out. Okay, and I can speak from that, from experience. Okay. Yeah, so we've done that. Okay, thank you. We're done now. Okay, excellent. Thank you. Okay. And here we are. Okay, good. Thank you. So again, just to recap purely, in avalanche breakdown devices, the increased temperature results in increased activity in the atomic structure, and the free charge carriers find it more difficult to acquire the critical energy to ionize other atoms. As a result, the breakdown voltage of avalanche diode increases with temperature. Okay. And here we have our illustration of just showing you characteristics of various Zener diodes. Now, please note, it's only applicable to certain various types of diodes. They're not all of this type. So you have some that will break down at 15 volts. You have some that will break down at 6.8 volts. And here's your knee that we're talking about, okay? Sometimes here it gives a smooth knee, okay? Here we have what here I would call this a smooth knee. Here we have a sharp knee, just drops. But here we have 4.7 volts, okay? And this is where you can have a diode that will break down to 4.7, 6.8 or 15 volts. Now obviously you can have them that will break down at a higher voltage, but you'll find that probably used for special work or etc. or rather expensive equipment. Okay. And now again, anode, okay, anode current, okay, and that's reverse breakdown, that's forward bias, okay, and that's reverse breakdown. Okay. So let me just go up a little bit, make sure we can get this in there. Okay. Okay. Let's bring the other part in to this, okay. Now here we have the anode Zener symbol, and you have your cathode, okay. Now you have an equivalent circuit RZ voltage Z. Okay. Now this equivalent circuit was used for a given purpose, but you know, for the life of me, I cannot remember offhand. So you have to excuse me. I do apologize. Okay. Now I remembered it before I began to put it on camera, right? So do forgive me. But that's the diode 1, diode 2. It's designed to produce a given effect. Okay. Okay. And this bit here, right now, this is designed for you to fill in one of the first useful, etc, 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 and this is what you would be writing up for yourselves. Okay, basically it allows you to recap what we've spoken about in regards to the text that was given. So by doing this and filling this in for yourselves, it enables you to understand the concept in respect of Mr. Zener and his idea at that time. And you can imagine trying to apply 7 million volts to a given material. Now it's interesting actually here, because what he has discovered is that if you apply a high enough voltage to an insulating material, that insulator can become a conductor. Okay, and that is what he has highlighted in his work and his theory, from my perspective. Okay. And now it is found that Zener avalanche breakdown mechanism reacts in different ways to change in temperature. Okay. In Zener breakdown, the tunneling effect increases with temperature, resulting in a greater flow of current for a given anode voltage. Okay. In avalanche breakdown devices, the increased temperature results in increased activity in the atomic structure, and the free charge carriers find it more difficult to acquire the critical energy to ionize other atoms. And this, as a result, the breakdown voltage of avalanche diode increases with temperature. Okay. And now here I've just given you an additional information from, I've done some additional research on the web and have added these to the video. Remember, you should always draw out the diagram with graphs when available. Okay, this is to support the information I have given above already. Okay, so again, this is just some additional information for your own edification, but this does not stop you from doing additional research for yourselves. Get familiar, know what you're talking about. Okay, draw out the diagrams, see what they've said. Now when you actually put some of these diodes to work for you on a, sorry about that, excuse me. Sorry about that. I was just looking for, when you actually begin to put some of your diodes on a board like this. Okay, it's a breadboard, right? Okay, and the breadboard actually allows you to, on one side is plain, and on side you have little pins that you can insert your diodes in. They will fit into this neatly without any problem at all whatsoever. And you'll find that you can build these. You can actually build some very interesting circuits with these breadboards using diode and components, and you can build regulators and etc. and so forth. Okay. Again here, I'm just going to go down Okay, so bear with me. I'm just showing you this here, okay? Purely for information again only, okay, for yourselves. Okay. So I'll just slowly go down, okay? Again, diodes used for clipping the AC waveform. And here we have an example of that, okay? And we have here power regulator. Now you can build all these circuits here on using this equipment, okay? You'll be surprised, you can build these circuits here used on this. And what the power source would be 9 volts battery, but you can make it up to 18 volts by linking 2 batteries together, okay? So the voltage is almost limitless basically, but keep it safe, okay? Safety, safety, safety please, every time. Okay, I think we're coming up to the final one now, and here you have voltage regulator. What this does, it limits the output voltage at this stage. So you can have this Zener diode, and you can have a voltage, maybe you might want 5 volts out here, so you can apply a given voltage here. That Zener diode will only allow 5 volts at this point. So let's say for instance we have 12 volts being applied across here. It will only deliver you 5 volts at this stage, because it will break down anything excess of that and maintain that voltage constantly. Again, do some additional research. So if you're interested in looking at the voltage regulators, look at how they have set up the voltage regulators and what type of voltage that your Zener diode would be equipped to operate at, okay? Alright, this is just the graph showing reverse breakdown, okay? You've seen something like this already earlier up before, okay? But that will do us for now, thank you, okay? And that will be it, okay? Thank you for your time. Now I hope you find this useful. Again, let me just make it clear. Use the information, do some additional research, write out the information for yourselves, draw out the diagrams. Now you can actually plot these graphs, okay? They can be plotted at the point at which the Zener diode actually breaks down, okay? So again, thank you for your time, and I hope you found this useful. Have a good day. Bye bye for now. Thank you. Bye bye.